In this video, I will do a node voltage analysis problem that requires two nodes. So if you haven't seen my one node example, I'll put the link in video description below, so you want to see that so you can understand the terminology and the plan here. So we have to start off by picking a ground. So I'm going to pick this bottom node as ground. We get to call that 0. We have a few other nodes. We can label them A, B, C. Those are all the nodes in totality, so there's 4 of them. There's only one extraordinary node, and that's B. Oh, excuse me, there are 2 extraordinary nodes, B and C. VA is known. It's 12 volts because we've defined the ground to be here. So, of course, this node A then is 12 volts higher than ground simply because of the voltage source. So what we have to do is we have to define currents at each of the unknown nodes, the extraordinary nodes, that is. So I will define all currents that leave the node. So we have 2 unknown nodes, so we need 2 nodal equations, one for each unknown node. So let's put here node B. We'll assume, of course, that we have a voltage VB and a voltage VC here. Remember, these currents that we've defined for each node are arbitrary. I could have picked them to have either direction. I just have to be consistent about how I treat them. I have to be careful that I add them up or put them on the right side of the equation properly. The next step is to use Ohm's law to convert these into expressions in terms of voltages and resistances and known currents. So using this sort of system, we'll use the IXY. It needs to be Vx minus Vy, so nodal voltage at X minus nodal voltage Y over R, the resistor of interest. So for I1, we have VB minus VA over 2 ohms. I2, VB minus 0 over 6 ohms. All those currents have to sum to 0. For node C, I4, the 1 amp source is negative I5. You see the current of the source points in the opposite direction to I5, so over here, negative 1 amp. And from C to ground, we have C minus 0 over 3 ohms. We will rewrite these 2 equations in a nicer form, a more helpful form. We're going to group them, right, because we have, let's just put here, there are 2 unknown voltages, VB and VC. We know VA is 12. 12. So we'll write these equations out better. So let's have a VA factor. VA in the first equation for node B, you can see there's a, I'm sorry, that should be a VB. VB has a factor of 1/2 from the first term, a 1/6 from the second term, and another 1/2 from the third term. And then the other unknown is VC. So we have here a minus 1/2, and that's it. Notice that every term here has units of amps because it's voltage divided by resistance. So it's a current. So this 12 divided by 2, well, it's actually a negative 12 divided by 2, is a negative 6. But when we push that to the other side of an equation, it's a 6 amp quantity. Same thing for the other equation. We have a negative 1 amp on the left, so we can push it to a 1 amp on the right. And then we'll have a VC. And what does VC multiply? Well, I see a 1/2 and a 1/3. They get added together. VB, I see a negative 1/2 term. Now I'm going to write this in a more helpful form. We'll do it in a matrix form. So in a matrix form, we're going to have VB and VC. Our constants are going to be this. And then we group things here like this. So this, you can do the math. It's a 1 plus 1/6, so that's a 7/6. And then this turns out to be 3/6 plus 2/6, so 5/6. So we can write a matrix like this. So notice that with two unknown nodes, we need two equations. And so when you have two equations, you get a 2 by 2 matrix here. I'm going to call this G because everything in here has units of inverse resistance, and so that's a conductance. I'm going to call this one a vector V, and then we'll call this a vector I. And we can solve this mathematically. We would write this as V, because that's what we're trying to get, right? V is G inverse times I. Let me show you how to do this in MATLAB. So I have a new script here. First off, I'm going to save it. We'll define a G matrix. For clarity, we'll get a new line. Now we solve for the voltages. This G, it's a left divide, so MATLAB understands this to be the same matrix multiplication that I wrote out here. It's G inverse times I. So if I run this, you can see my values for V, 7.61 and 5.76. Now, we want to double check this, so what will we do? Well, we'll recognize that VB is the first element of V, and VC is the second element. So that'll help us out a little bit. It'll be a nice little shortcut. And so I'll just check here. I1, this is VB minus 12. I2 is VB minus 0 over 6. So if I run this, it tells me the currents. I1 is negative 2 point something. I2 is 1 and some change, and I3 is 0.9 and some change, and I3 is 0.9. If I sum these together, I get a result that is very, very close to 0 when you compare it to the rest of the currents here. So we could recognize that as a numerical artifact. The sum of currents leaving node B is essentially 0, and that exactly satisfies our expression there. So now we know the voltages at each node, and we could calculate any current or any voltage or power we want in this circuit. So there's a brief illustration of a two-node nodal voltage problem.